Okay, so on to chapter 3. Again, relative to what you need to know for your exam, here's some kind of hints. This was the history, right, of kind of astronomy as we know it. So Ptolemy actually is a player, and Ptolemy I like to kind of think as being the last person to of note to put the Earth, have the geocentric model. He's very famous. And he is actually famous for creating this kind of, you see here being drawn, the Earth in the center. Oh, let me go back. Okay. The Earth in the center and having the planets orbit the Earth, okay, geocentric model, and the planets then would go do these cute little epicycles that you see as the little circles. And the reason Ptolemy needed to do that was because astronomers and everybody were watching watching these wanderers we now know as planets wander in direct motion across the sky. Then every once in a while they would go backwards, and so he created these little epicycles to explain this retrograde motion. Okay, so that's Ptolemy. And then there's a figure from your textbook I'm putting up here that actually this is why we see the retrograde motion that Ptolemy tried to explain using epicycles. We see retrograde motion, and I have it kind of down there later, I think, or maybe now. We see retrograde motion of planets as our planet overtakes that planet as it orbits the sun. So retrograde motion is explained here in putting the sun at the center of our solar system, having the planets orbit the sun, and having the Earth in this case go faster in its orbit relative to Mars. And so when it overtakes it, Mars appears to go backwards against the background stars. And it's a very similar phenomenon, and I kind of talked about this in lecture. It's very similar to when you are driving down the road and you're driving in a fast lane, the left lane, right? And when you are looking at a car that you're coming up upon, and it looks like it's going the same direction as you against the background stars. As you overtake the car, it appears to kind of go backwards, okay, against the background, and then after you've overtaken it and you're clearly past it, it again starts to kind of look like it's going the same direction against the background. So it's something it's kind of a sensation sort of thing. And parallax. Parallax is a change in the position of an object that's relatively close or nearby relative to the background. And the figure I used in lecture is going to be shown up here, is basically that guy and that the man and the woman looking at the same tree, and they're looking against their background actually happens to be mountains, and they are, as they kind of are different positions relatively speaking, they see that tree kind of at a different location. So you see the guy sees the tree against that part of the mountains, and the woman sees the tree against that part of the mountains. So parallax will only work like you're seeing here if there is an object that is relatively close, okay? And we are changing our position. So here change of position would be indicated by those two people at slightly different positions. So we see that parallax of the tree against the background mountain. Okay. So the next term you're going to see is Copernicus then actually kind of see, I'm kind of wimping out here. I'm pointing, for Copernicus, I'm pointing to the heliocentric model where the sun is at the center and the Earth orbits the sun and Mars orbits the sun and all the planets orbit the sun. Okay, but as you see in purple here, what Copernicus still didn't quite, he still couldn't anticipate apparently where the planets would be, because his model, though it was correct with the sun at the center, it was not correct with regard to the shape of the orbits of the planets. So it took a little bit of doing to get past this perfect circle sort of thing. So Tycho Brahe, again, subscribed to the heliocentric model, okay, putting the sun at the center and the planets orbiting the sun. And here I have Tycho Brahe had lots of great observations, and I kind of think of him as kind of a rich person with lots of money and an awesome telescope for the day. And so he hired Kepler, and Kepler then actually made some definite breakthroughs with regard to understanding why the planets, understanding more about the planet's motions about the sun. And so to me, then Kepler kind of worked off of Brahe's observations. And so he came up with these 3 laws, okay, Kepler's 3 laws that are limited to how the planets orbit the sun. And so hopefully, as I'm talking about their observations back in the 1700s, you realize that, or 1600s, you realize that they did not know yet of, they knew of Saturn, but that's where it stopped. They didn't know of Uranus and Neptune, let alone Pluto, right? So his first law, if you have to draw on a test, is basically kind of the shape of the orbits of the planets. And the shape is an oval or an ellipse. And one thing about ellipses is they have a feature called a foci. And so what Kepler's first law says is that the shape of the planet's orbits about the sun are ellipses, not circles. That's a big hairy deal. And that kind of the sun is a little bit off center at one sweet point of an ellipse called a foci. Okay, his second. Oh, by the way, I also in purple there you see the 2 important terms, perihelion and aphelion, that kind of remind me of perigee and apogee with regard to the moon Earth system. But because the sun is off center, not the center of a circle, sometimes the planet is in orbit about the sun and it's closer to the sun than other times in its orbit, and we call that perihelion. And when the planet is farthest from the sun, we call that aphelion. So his second law, Kepler's second law, is kind of worded kind of weird, okay? But basically he said if you take time segment, and I'm going to show you here in a minute, time segment AB and time segment CD, okay, and those time segments are equal, that if you go ahead and sweep out areas, like I see that red mark there, okay, sweep out areas, those areas are equal. Now, do you see where the segment AB is longer in the same time as the planet orbiting the sun clear out there at CD? So CD, the planet doesn't cover as much ground. And that actually goes back to creating the same areas. So related to that then, near or at perihelion, a planet is moving fastest, and at aphelion, a planet is always moving slowest. So equal areas and equal times, that's what that's all about. The biggest consequence of that is, like I said, planets move fastest, and it's a gravity thing. You can almost feel it. As a planet approaches the sun, it goes, and then it goes back out again, okay? His third law is probably my least favorite, okay? And I apologize in advance. I think I still haven't fixed it yet. You're going to see it kind of blocked out a little bit. But basically, Kepler, in his third law, looked at the data. He estimated, actually, Copernicus had already estimated the average distance between the planets and the sun. And he looked at that average distance and related that average distance to how long it would take that planet to orbit the sun. And again, I think this is blocked out for you, but if on your test, if you just put p squared is equal to a cubed, that would be great. Because basically, if the period, the amount of time it takes for a planet to orbit the sun is in years, and if its average distance is in astronomical units, then you get this p squared is equal to a cubed for all the planets. Pretty darn cool. Okay, that's Kepler's third law of motion, but it's just motion as it relates to planets orbiting the sun. All right, what else we got? In green down there, we've got being drawn, we have Galileo. Galileo was not the first to use the telescope, but he was the first to point it at celestial objects and study them. And one of the things you see, he saw imperfections in nature. And it's funny that there used to be a time when, because science just shows, to me, there's beauty in imperfections. Okay, but there used to be a time when, like, nature is perfect, people. So anyway, the fact that he saw blemishes on the sun, we call sunspots, And the fact that the moon was not kind of entirely smooth, he saw craters and pocks on the moon, got people to thinking, well, there you go. Okay, things aren't always perfect. Galileo also, remember in your textbook it shows you that he tracked, and it looks like a star, but he tracked the planet Jupiter, and he saw these satellites orbiting Jupiter. These 4 moons or satellites orbiting Jupiter. Isn't that cool? And anyway, we call those Galilean moons. And then he also saw the phases of Venus, and I went ahead and brought that in for you. That's in your textbook. So that kind of looks like a sliver of a crescent all the way to a full. Those are the phases that we see Jupiter go through. And like I'm saying underneath that figure, we can only see Venus go through these phases if Venus is also orbiting the sun. Only works with a heliocentric model. So the last couple up there, I have Occam's razor. And Occam's razor actually, we kind of touched on it when we talked about Ptolemy's epicycles. We said, boy, that is getting complicated, making these little loop-de-loos to epicycles to explain why planets appear to go backwards. And one of the hallmarks of a correct scientific thinking is that it is straightforward. It's as simple as possible. Things that are trying, if your model is too complicated, like Ptolemy's epicycles, what you're trying to do is probably force fit your observations to what you want them to be. Okay, so of course, keep it simple. Stupid is kind of what we're saying when we talk about Occam's razor. Simplicity is the best. And speaking of the best, one of the things I want to kind of instill in you, or kind of reinforce in you if you weren't already familiar, is that there is definitely a difference between a hypothesis and a theory. So in the scientific method, what a hypothesis is, it's that original kind of best guess, and we work with hypotheses for a long time, gathering, running experiments and things like that, until it can ultimately be elevated to a scientific theory.